Okay, this is the pre-class lecture video for Friday, November 16th. So now that we've talked about in class in terms of alkene functional groups, how to make alkenes, either by dehydration of alcohols or by doing E1 or E2 and primarily E2 eliminations of alkyl halides with usually NH2 minus or tertiary butoxide. Now let's talk about reactions of alcohols. And this is going to take several days, reactions of alkenes. And this is going to take several days to talk about all the possible reactions that you can get with alkenes. So we're going to start with what are called addition reactions. And in an addition reaction, I'm going to add an XY molecule, a molecule that has these two parts to the double bond, and I'm going to end up adding the X part to one carbon and the Y part to another. And so I'm doing addition because two molecules come together to form one. And notice the double bond becomes a single bond. Now there's going to be lots of nuances with this, like which carbon does the X group add, and how does the X group add? Does the X and Y group, do they add to the same side of the double bond? Do they add opposite sides of the double bond? Do they add a 50-50 mixture of both? But let's just start with something fairly straightforward in terms of adding X and Y. And I'm going to start with 2 for this class using HCl, HBr, HI, and then I'll broaden this out to HOH, or in other words, water. So first let's look at the double bond and remember what a carbon-carbon double bond looks like. We've got a pi bond and a sigma bond. So we've got a carbon held together by a sigma bond, and then the two p orbitals overlap to form the pi bond. And then we've got our other groups then in the same in a plane. Now, in terms of classifying a double bond, I classify a double bond as a nucleophile. In other words, something that is electron rich. And what's the source of the electron richness in a carbon-carbon double bond? Well, it turns out these two electrons in the pi bond. That's the source of electron richness to make a carbon-carbon double bond a nucleophile. So that means that carbon-carbon double bonds will react with electrophiles. And the electrophile that I'm going to react this with first is H+. So let's look at the Lewis dot structure picture of what's happening. If I add H+ to a carbon-carbon double bond, I can take this double bond and give that pair of electrons to that H+, which means that either carbon 1 or carbon 2 is going to bond that hydrogen. Now, let's not worry right at the moment whether it's going to be carbon 1 or carbon 2. In this case, I'm not using a specific alkene, so we'll consider them to be the same. So if I attach the hydrogen then to carbon 1, what's going to happen to carbon 2? Well, carbon 2 kind of gets the shaft here because its pair of electrons have been used to bond the H+. And so therefore that carbon is going to become a carbocation. And so I've changed the nucleophile of the double bond into now a carbocation intermediate. Okay? And the transition state for this, if you wanted to write that, I would write the transition state like this, where the hydrogen is partially bonded to one of the carbons. The carbon-carbon double bond is partially breaking. And then you've got a buildup of charge, delta plus, on that carbon. And that hydrogen's on its way from +1 to being 0 formal charge. So this would be the transition state that I would kind of write for this reaction. Now, you might say, will the hydrogen bridge over both of these two carbons, kind of like it did with the hydrogen migration, a H2 or a 1,2 hydride shift? And the answer is no. The hydrogen's going to pick a carbon to add to, or actually the carbon is going to pick, one of these two carbons is going to pick the pair of electrons up to add to that carbon or that hydrogen, but for the most part, the hydrogen's not going to bridge. So when I add H plus to a double bond, I make a carbocation. And then if I'm reacting, let's say HX, and HX could be HCl, HBr, HI, etc., then that nucleophile, that halogen atom, is simply going to come in, add to that carbocation, so that now I've added my H and my X atom across the double bond. Okay. And so, for instance, if I was to take this alkene and react it with HCl, how would I write that mechanism? Well, notice I'm starting with a symmetrical alkene. In other words, one where the same groups are attached to the double bond. I'll make it a little more complicated with an unsymmetrical alkene here in a moment. But I would take this pair of electrons and then use it to bind the H+. So the HCl is going to split apart, and we're going to have H+ being bonded to one of these two carbons. So I would go through, let's say, this transition state. To then form my carbocation intermediate. Okay. Then in the second step, my chloride will come in, add to that carbocation. Can we write the transition state for that? And then the final product would have that would be the final product where I've added H and Cl across the double bond. And this mechanism would be the same whether it was HCl, HBr, HI. Normally we don't do this reaction with HF, so it's usually just those three that we would do this reaction with. Okay, so this is an example of an addition reaction. And it's actually something called, more specifically, electrophilic addition. And the reason that it's electrophilic addition is because it's started by an electrophile adding to the carbon-carbon double bond. And so that nucleophile of the carbon-carbon double bond has to react with the electrophile of the H+. Okay, so this is an example of HX addition to a carbon-carbon double bond. And I've started with the simplest case where I have a symmetrical alkene, so it didn't matter whether I added the H to the left carbon or I added the H to the right-handed carbon. Okay, but now let's make this a little bit more difficult. So let's take and make the alkene unsymmetrical by reacting this propene molecule with, let's make it HBr in this case. Okay. Now, I can actually get two different products for this reaction. When we do addition reactions, we have to think of them in two ways. Can I just write the product of the reaction, or can I write the mechanism? Because the reality is you're probably going to have to do both for the next test. So if I have carbon 1 here and carbon 2, I could add the H to carbon 1, so one of the possible products that I could get. Now, the net result is we lose the double bond, so I could add the H to carbon 1 and the Br to carbon 2. Or the other possible product is to reverse that and add the H to carbon 2 and the Br to carbon 1. And so that gives us these two possible products, which I'll call product A and product B. Now, we've done reactions before where we've gotten multiple products. And if you're psychic, you can probably think about what the next question that I'm going to ask you. Got it? It's going to be, well, what's the major product, A or B? And then if you're even more psychic, you can probably think about the next question I'm going to ask, which is going to be why. Well, without answering whether A or B is the major product, let's write the mechanism for this. So let's add H plus to C1 and write the resulting carbocation intermediate. So here's my first intermediate if I add H plus to carbon 1. Now let's add H plus to carbon 2. What am I going to get? And then, of course, I would add my, what am I adding? Br minus. Okay, I don't know what happened to my pen, but it just died. So now I'm going to go ahead and add my Br minus to this carbon, the carbon 2, and that's going to make product A. And I'm going to go ahead and then add the Br minus to carbon 1, that carbocation, to make product B. Now, can you tell me which one of these products is going to be the one that's formed as the major product? Now let's think back about how we've done this in the past. In the past, we've usually either gotten the major product to be the most stable product. Let's see, where was that? Zaitsev's rule was an example where we made the most stable product. Or we also did reactions where we went through the most stable intermediate. What would an example of that be? Free radical halogenation, where we would get our major product because we went through the secondary radical versus the primary radical. Well, here's the thing. I don't know which of these two alkyl halides is more stable because I don't have a rule for that. I don't have a rule that a secondary bromide is more stable than a primary bromide. But here's what I do have. I have a rule that a secondary carbocation is a lot more stable than a primary carbocation. As a matter of fact, I wouldn't even let you draw that. But the rules don't necessarily count for me, so I will write this primary carbocation to show you. So actually in this case, I wouldn't form the primary carbocation because it's too unstable. Instead, I'd form the secondary carbocation, and so therefore product A would be my major product. I doubt that I would see much product be in this reaction at all. Okay, so when I'm reacting HBr or HCl or HI with with an unsymmetrical alkene, I actually have to take into account that I'm going to form the more stable carbocation intermediate, and that's going to give me the major product of the reaction. So let's do another reaction here. Let's do cyclics, because I like to do this with cyclohexanes. So let's say I was to react cyclohexane, or 1-methylcyclohexene with HBr. What would be my two possible products of this reaction? Well, let's call this carbon 1, this carbon 2. So my two possible products would be to add the H to carbon 1 and the Br to carbon 2. And the other possible product would be to add the Br to carbon 1 and the H to carbon 2. Okay, and that's how we would draw out the products if that's all I asked. If all I asked you was, hey, write the products of the reaction, this is what you do. You wouldn't have to go through a mechanism. But if we had to go through the mechanism, what two carbocations would I form? Well, adding the H plus to carbon 1 gives me a secondary carbocation, and adding the H plus to carbon 2 would give me a tertiary carbocation. And notice that when I react my Br minus with a secondary carbocation, that takes me to form product 1. And when my Br minus comes in and adds to tertiary carbocation, that gives me product 2. So the halogen added to the carbon that was the carbocation intermediate in this mechanism. So which one of these two products is the major product? Well, I got tertiary carbocation versus secondary. That's going to make this product the major product, and then this product is going to be the minor product. Now in this case, both products are going to be formed. It's just you'll get more of the 1-bromo 1-methylcyclohexane versus 1-bromo 2-methylcyclohexane. Okay, so that's what the major product of the reaction is going to be. Now, before anybody knew about the mechanism of the reaction, a Russian chemist named Markovnikov came up with an empirical rule to predict the major product of these kinds of reactions. And what Markovnikov said was that in an addition reaction of H and let's say X to a double bond, what he said was that the hydrogen goes to the carbon with the most hydrogens. So that was what he empirically observed every time he did an HBr, HCl, HI addition to a carbon-carbon double bond. He always saw that the major product of the reaction was the one where the hydrogen went to the carbon with the most hydrogens, which then leads to the paraphrasing of this rule. I call it the them that has gets rule. Those carbons with the most hydrogens gets the hydrogen. And then, of course, the other carbon, that gets the halogen. So the Markovnikov came up with this empirical observation, and it became Markovnikov's rule. Okay, and so Markovnikov then came up with this rule that allows us to predict the major products of the reaction. Now we know why that's the case, because we go through a carbocation and we know the more substituted carbocation, which by the way is the carbocation that has the less hydrogens attached to it, or came from the carbon with the less hydrogens, that one gets the bromine and the other carbon gets the hydrogens because that produces the more stable carbocation. Okay, so Markovnikov's rule helps us predict what the major product of the reaction is, but really it's the mechanism that shows us why we get that particular major product. And I'm going to broaden Markovnikov's rule out because right now I'm adding an H plus and an X minus for chlorine, bromine, or iodine. I'm going to say later on as we go through this that if the electrophile adds to the carbon with the most hydrogens, and then the other group, so this is going to be our nucleophile part, that if that adds to the carbon with the least hydrogens, that it follows Markovnikov's rule. So we're going to broaden Markovnikov's rule out later to incorporate other alkene addition reactions that don't simply involve H+. But the ones I'm doing today are simply H+ and then nucleophile, or X- in this case. Okay, so that's how we can predict the major products of the reaction, is by using Markovnikov's rule. And certainly once you get past the first step of taking your double bond and reacting it with your H+, once you get to this step and you get your carbocation, well, that's just SN1. That's all that reaction is just an SN1 mechanism. Okay, so we could add HCl, HBr, HI to double bonds, and we could predict the major product. Well, are there any trick questions? Oh, there are tons of trick questions when it comes to these kinds of problems. And they're really not trick questions, but what happens, what would be the major product of this reaction? Well, in this case, neither hydrogen has any hydrogens. And if I wrote the mechanism of this out, I would get the carbocation on the top carbon, and I could also get the carbocation on the bottom carbon, by adding the H+ to the top and bottom carbon. But in this case, what do I have here? I've got a tertiary carbocation, and here I've got a tertiary carbocation. And so in this case, remember, tertiary carbocations are the same stability whether they have a methyl, ethyl, propyl, or a 100 carbon chain. So just the fact that it's tertiary makes these two carbocations of equal stability. So that means that in this particular case, I would get a 50-50 mixture of these two addition products. So actually I would not have a major product of this reaction. So Markovnikov's rule only works if you have an unequal number of hydrogens attached to the carbons attached to the double bonds. Okay, so in this case there would be no major product of the reaction. Okay, so is this the only thing that we can add to double bonds? No, we'll probably finish up adding to double bonds maybe just before Thanksgiving. So we still got a couple of days worth of reactions. But I want to do the second reaction. Yeah, we'll do this one. So we'll take cyclohexene and I want to add water to it. Now I have a problem. What I'd really like to do is I'd like to add the H OH across the double bond to make an alcohol. That's what I'd like to do. But will an alkene react with water? Will these two react together? If you said no, you're right. But why won't these two react together? Well, we said this is a nucleophile. This is electron rich. And what's water? Water is also a nucleophile. And in the chemistry world, two electron rich species, they don't donate to each other. It's only electron rich to the electron poor. So in order to make this reaction go, I'm going to need to add an electrophile to this mix, because I want the electrophile, I want the double bond can only react with an electrophile. Okay, and so what's that electrophile going to be? Well, the theme for the day is add H plus to a double bond. So it's going to require that I add H plus and H2O to the double bond. And so the first step in the mechanism is going to be to have the double bond react with the H plus. That's going to give me this carbocation. And now the whole water molecule is going to come in and add to that carbocation. It kind of feels like deja vu. And what happens in the final step? Break the HO bond. Lose the H plus. And now I've generated my alcohol. I've net added HOH across the double bond. Problem is, the H that's on there didn't come from H2O, it came from the acid catalyst. Okay. Now, this reaction, kind of boring because we've seen it before. We've seen this part before, right? Water adding to a carbocation to form the oxonium ion to lose the H plus to give you the alcohol. That was on the last test. That's how long ago that was. So this is basically SN1 addition with water. But here's what I will point out. Because if you're saying, yeah, but I think I've seen this whole thing before. Well, you saw the whole thing on Monday. Because what happens if I take an alcohol and I treat it with H+? I form an oxonium ion. And then what happens if this is a secondary system so that the water leaves and I form a carbocation? And then what happens when I lose the beta hydrogen from the alpha carbon to give me the double bond? So this reaction, this addition of water to the double bond, is the reverse. So the reverse reaction is dehydration that we saw on Monday. So what do you think the forward reaction is called? It's called hydration. Addition of water to a double bond. And so in this case, I'm doing the reverse mechanism. So that's why it seems so familiar, is simply the fact that it's the reverse of dehydration. Now, hydration follows Markovnikov's rule because I've got H and a nucleophile. So I could take my double bond here and react it with H plus H2O. And I could write both possible products that are formed, because the net result of this is to add H and OH across the double bond. So that means I could add the H here and the OH here, or I could add the OH there and the H there. Which one's going to be the major product? If you said this one, you're wrong. It's this one. The carbon with the most hydrogens gets the hydrogen, and the other carbon gets the nucleophile, which in this case is water that then becomes an OH. Okay. If I was to do the mechanism for this, react the double bond with H plus, writing the mechanism for the formation of the major product. In this case, I'd write there, add my H plus there. That would give me a tertiary carbocation. My H2O comes in and adds to that carbocation to form then my oxonium ion. And then I lose my H plus to give me the final product, which is the Markovnikov product of that reaction. Okay. Let's see. One last question and then I'm done for the night. What is H plus in this reaction? What is its role? Is it a reactant? No. Is it a product? No. It's a catalyst. It was a catalyst in the dehydration reaction, wasn't it? Yeah, so it's a catalyst in the hydration reaction. I was mistaken. I have one more thing I want to end with here. Here's how I would write this reaction. That's how I would actually write the reaction, write this reaction. So forwards direction, this is hydration, reverse reaction is dehydration. I put the H plus over the arrows because it's the catalyst. And the reverse reaction would take some heat to get the dehydration to occur. Now, how do you actually force the reaction to go to completion? How do I get 100% hydration if this is an equilibrium reaction? And how would I get 100% dehydration if I wanted to go in the reverse direction like I did on Monday or Wednesday? Well, this is where I use Le Chatelier's principle. If I wanted to force the equilibrium to form mostly or to 100% hydration product, what would I do? Well, I would use an excess of water, and then Le Chatelier's principle would push that equilibrium to the formation of the alcohol. How would I push the reverse reaction to give me 100% dehydration? And if you don't quite see that, here's the reverse equilibrium. Well, in this case, there's nothing I can add to the reactants to push the equilibrium, so I would end up removing one of the products. And just to give you a little bit of insight as to how you do this in the lab, we know that the boiling point of water is 100 degrees. And we know that the boiling point of alcohols is higher than the boiling point of an alkene because an alkene is a hydrocarbon. So what I would do is, if I wanted this reaction to go, I would adjust the reaction temperature to just below the boiling point of the alcohol, so that way when I form the alkene would then distill, and I'd be removing products and force the equilibrium all the way to the right. And so a lot of times you can basically set up a distillation apparatus, add your alcohol to there's my distillation apparatus, add the alcohol and the acid together, and then heat it to just below the boiling point so that the alkene then basically distills over and is collected. And this, in an industrial sense, this is actually very, very easy to do because you just keep feeding in alcohol, because the acid is a catalyst, so you keep feeding in alcohol and it keeps producing alkene. And so it's very easy to do, an industrial dehydration of an alcohol to form an alkene. And actually, that was one of the sections in the textbook that you hopefully read earlier on in the week. Okay. But one of the things I didn't talk about on Monday was the idea that this is an equilibrium. So how do you push the equilibrium towards the formation of the alkene? Well, you just take advantage of the natural boiling point differences. And then how do you push the equilibrium towards the formation of the alcohol? You use Le Chatelier's principle and add an excess of the water. Okay, so that's what we'll talk about on Friday and do some problems. Markovnikov addition of HX, Markovnikov addition of H plus H2O in the hydration reaction. And those are going to be our opening reactions that we talk about in the reactions of alkenes, namely the electrophilic addition reactions of alkenes.